Okay, so here's an algorithm of finding a Jordan basis for a nilpotent operator, which has this nice feature that if you make a mistake on the way, or if you have some small omission, as long as it's not an important computational mistake, you can always you can adapt the previous quick methods and keep moving forward until you construct a Jordan basis. And you don't need to follow a rigid set of instructions always the same way. So it follows this idea. That's the very description of what a Jordan basis looks like. What's a Jordan basis? That's a basis where you have one vector and then you apply the nilpotent operator to that vector. You get another one and you get another one and then you get another one and eventually you get 0. But we are constructing this basis step by step. Of course, we want in the end one that goes to 0, but in the process we may not have that. So I'm calling this a thread. Both of these, I'm calling them threads, but I'm calling this one here an open thread, and I'm calling this one here a closed thread. So the only difference is it's closed because I know already that z is mapped to 0, and here before I didn't know that. Maybe it is, maybe it's not. In any case, the length of the thread will be just the number of vectors that we have here, and is the number of vectors that we have here. We don't count 0, of course. And the tip of the thread is the last vector here, and the base is the first vector here. And we'll most of the time be dealing with a collection of threads. Maybe it's a very simple collection. It has only one thread on it. And also threads can be very simple. They can have only one vector on them or even be empty, but that doesn't really help. So, and the size of a collection is how many vectors we have in it. So if you understood what a Jordan basis is, then you already have a hint. If you have a collection whose size coincides with the dimension of the space, and they're all closed threads, and all vectors in the collection are linearly independent, and that's a Jordan basis. Actually, it's equivalent to being a Jordan basis. And the algorithm we are going to look is an algorithm that starts with some collection of threads and applies some operations to them and makes them longer and then makes them thinner and makes them longer and then thinner until in the end it gives a Jordan basis. So here's the algorithm. And it's not even a deterministic algorithm. You don't have to apply one operation at each time, one specific operation. There's just two operations that you can apply at any point, which is you stretch this collection of threads or you reduce this collection of threads. So let's describe these two operations one by one. So stretch a collection of threads is something you can do if at least one of the threads is still open. So if one of the threads is still open, you stretch it. Now you can guess what it means to stretch. You just apply n to the tip of the open threads. So you have this vector z here, that's an open thread. You apply n to the vector, and two things can happen. Either this thread will increase, the length of the thread will increase, or the thread which was open will now become closed. Okay, this is what can happen. And the other operation that we can perform is to reduce a collection of threads. How can you reduce it? That's something you will do if the tips of the threads are linearly dependent. Okay? And how do you do that? You sort this collection from longest to shortest. If two threads have the same size, then it doesn't really matter, the order. And then you find which ones are linear combination of the previous ones. How do you do this? How do you find which vector is a linear combination of the previous ones? You just write those vectors in columns, one after the other, perform row reduction, and you see this. And then you subtract the corresponding linear combination at the base of this thread. So the base is the very first vector of the thread. But of course, if two threads don't have the same length, then this will not be very helpful. So you have to actually pick a vector which is at the same distance from the base. So you take a vector from the same distance from the to the tip as the current one that you want to reduce. That's the concerned thread here. And then you subtract the linear combination of the vectors from the previous threads, which are longer, to that base of the thread. And now you recompute the entire thread, which will basically mean that this linear combination will be subtracted at every level until you arrive at the tip of the thread. So this will propagate throughout the thread, and at some point this thread will become 0. At the tip, it's guaranteed to be 0, because this is exactly how you chose the linear combination, just so that this would happen. Okay? But maybe it will happen before. Maybe it will happen before. And this definitely causes the size of the collection to decrease, because at least the tip of this thread will become 0, so this thread will become shorter, or it will close this thread. Maybe it will become shorter and be closed. Okay. So this process must stop. Okay. Now I claim that this process must stop. And why does it have to stop? Well, because we cannot stretch forever. Each time we stretch, the longest thread will become even longer, or a thread which was closed, which was open, will become closed. So we can't apply this enough many times, because we know that within a thread, we know that already, vectors within a thread are linearly independent. Our operator n is nilpotent, so we can't have a very long chain of vectors which never arrive at 0 if we apply a nilpotent operator to it. So we cannot stretch enough infinitely many times. We can stretch a number of times which is bounded. In a very brutal bound would be it's bounded by the dimension of the space plus the number of threads. And in between two stretches, we cannot do reductions infinitely many times either, because if each time we do reduction, we reduce the size of the entire collection. So again, the process must stop. When it stops, what do we have? Well, it stops means we can't go any further. So it means we cannot reduce. Cannot reduce, that means the tips of the threads are linearly independent. And we cannot stretch either, which means all the threads are closed. And now, in order to conclude the proof that this algorithm gives a Jordan basis, you just have to verify that the whole collection of vectors is linearly independent. Well, actually, you need to verify a little more than that. Let me skip this part here. This part is quite tedious to verify and also very standard. So I invite you to read the proof here in the PDF that if this is a collection of threads and these vectors here are linearly independent, then the entire collection is linearly independent altogether. So if these are linearly independent, then we know it's a very simple exercise of linear algebra that these will be linearly independent and these will be, that we know. And also because this is a thread, we know that these are linearly independent. But in fact, we can say much more than that. We can say that the entire family is linearly independent. Let me skip the proof of this. It's very standard and very tedious. You can read it here in the PDF. And now, just to conclude, we know that what's this operation of reduction? Reduction consists in adding multiples of some vectors in the collection to some other vectors. And we know that when we have a collection of vectors and we do this operation, we add multiples of other vectors to some vector. It doesn't change what is the subspace spanned by the entire collection. In order to change it, the only thing you can do to change it is add minus a vector to itself. Then obviously this can reduce the space, the subspace that is spanned. So it doesn't change the space that's spanned. And when we stretch, we only incorporate more vectors into the collection. So the space that we span, it can increase actually. Therefore, it's enough to just start with a collection that spans the whole space. Okay? So if we start with a basis, or whatever collection that spans. You can start with something much larger than a basis. And in the end, we'll get a basis which forms closed threads. And then this will be a Jordan basis, as I pointed out already. And now so this concludes the proof. The proof is finished, but just some remark that comes from the proof is that we don't actually have to start with a family of collection of vectors that spans anything. If we start with a smaller set, then maybe this whole procedure will not give us a basis in the end because we will not have many vectors. But then we can, at any point, we can just add more threads to the collection and continue the game. So it's not a very rigid procedure. We can at any time incorporate more vectors, add some more thread, and keep doing reduction and stretching. And if the new vector we add is not in the span of the previous vectors, then the set that you span is increasing. So even that has to stop as well.